So filters are linear time-invariant systems. This means that they fulfill the following properties. If f of x of n is our filter function of input signal if x of n, then we have linearity. So for two signals x1 and x2, if we apply this filter function on the sum of these two signals, is the same as applying the filter to the first signal and add to the filter of the second signal. Yeah? If we have a factor of a, so if we are filtering a multiplication of the input signal with a factor a, this is the same as to filter first the signal and then multiply with the same factor a. So which means that we can draw out sums and factor out of our function. And it's also time invariant. So if y of n is equal to the function or filtering function of x of n, then we have for a delay of n0, so y of n plus n0, this will be the same as filtering our signal x at time n plus n0, which means that our function stays the same no matter when we apply it. So FIR filters the finite impulse response. So a simple finite impulse response filter, an FIR, has a difference equation like the following, with x of n is the input of our filter and y of n is the output of our filter. So here we have x of n, here we have y of n, and we have the sum, and going to 0 to capital L, so we have this b of m times x of n minus m. So observe that this is the convolution of the signal x with b of n. And here the b of m are the coefficients of the filter or its impulse response. These are commonly also referred to as steps because the system can be viewed as stepping a delay line as seen in the picture below. So the difference equation is also how usually filters are implemented in MATLAB, Python and other programming languages. So a typical block diagram of a finite impulse response filter is shown here. So we have our input signal, this is the output, we have our delay blocks, we have this multiplication, we have this additions, and we have here this block diagram of FIR. Observe that here the blocks with z to the power of -1 are implemented with a delay by one sampling interval, so it's not a multiplication with z to the power of -1 as we would do in the z domain. So after the first delay block z to the power of -1, here we will have x n minus 1, and after the second delay block we have x n minus 2, and so on. So each delay block memorizes the value from the left for one sample clock cycle and releases it to the right at the next sample clock cycle. Hence they delay samples by one sample clock cycle. So the z transform of our difference equation of our convolution, so here we have our convolution, so if we apply the z transform, we will have this here with this result. So now we can compute the transfer function, so we will divide output in the z domain by the input in the z domain, and that is the transfer function defined as the output divided by the input, and we end up with this equation here. So this is the transfer function, the output divided by input, and is given by here. And we have here, we can observe that this is the z transform of the coefficients b of m. So this is the z transform of the impulse response of the FIR filter. So now we can obtain the frequency response so that we can see which frequencies are attenuated and which are not from our transfer function of the filter if we replace z by e to the power of j omega. So what we are doing here, we have our transfer function in the z domain, and we want to have a frequency response. We will replace z by e to the power of j omega, and we will have this sum here. And since e to the power of j omega is a complex number, our frequency response is also complex. So hence is a complex number for each frequency capital omega. Usually it is plotted as magnitude plot and a phase plot over frequency. So its magnitude tells us the attenuation at each frequency, and the phase, its phase shift for each frequency. So using these two plots or two properties, we can design our filters with desired properties. For example, a stop band at given frequencies, and MATLAB and Python function to generate magnitude and phase plot for a transfer function or signal. We can use FracZ as we already used before. So I recommend, if you want to go deeper into the frequency response of filters and a bit of a revision of filters in the you can take a look at the Guitars AI GitHub on the multi-rate signal processing notebook number 3, the frequency response. There are also some video tutorials, and there you can take a look. So there will be some examples on how to obtain the frequency response of a black box system using noise, using the sweeping sinusoid. So frequency response, relations between the Z transform and DTFT, examples, revision on cascading filters, and also here there is a revision about the ideal low pass filters, frequency response, impulse response, delay. So you can take a look at Guitars AI GitHub, at multi-rate signal processing notebooks and tutorials.